Awesome. Hey guys, we're gonna overview a lot right now. Um, Basics, special relativity, Lorentz transformations. Let's do it. The most important aspect is remembering that we're in a coordinate system that is dependent on reference frame. So for instance, x comma t is the outside observer or the stationary reference frame. And stationary is relative, of course. So you can think like Earth reference frame. Obviously, if you're in the sun's reference frame, the Earth is what's moving. So you have to be careful of what's moving, what's not. And then x prime, t prime is the moving reference frame. And the point is that the space-time interval, which is this is the space-time interval, is the same in both reference frames, and we're going to actually calculate that today to show it. Now, the space-time interval has a physical meaning. You can think of it as the distance traveled in space and time. But the issue is that like if you have space only, meaning if I go 5 meters in the x direction and 4 meters in the y direction, then I go a distance of the square root of 5 squared plus 4 squared, which is the square root of 41. Am I doing my algebra, arithmetic correctly? Yes. Meters, which is approximately, the square root of 36 is 6, so I'm going to guess around 6.3 meters without doing this with a calculator. Something like that. So I went a total displacement of 6.3 meters, right? I'm now 6.3 meters away from where I started. Cool. So basically you'd say like dx squared plus dy squared equals, ds squared, right? You'd say the space-time, the space interval, ds, right? ds meaning delta, d means delta, right? This is like delta s, right? Change in position is that. But in space-time, it's not that way. So this is the space-time interval. And the reason is, you might remember, is that this comes from the fact that you need the speed of light to be the same in both reference frames at the same time. And if this were the case, if this is Euclidean geometry, this is your standard, a squared plus b squared equals c squared, no funny stuff, this would not be the case. Because if I start moving, then moving through time and space at a speed, then the velocities would just add normally, and we wouldn't get that the speed of light is the same in all reference frames. So for space-time, what we get is, of course, this. We get that it's uh, t squared minus x squared, or technically the change in t minus the change in x squared, not plus. For space, it's plus. For space-time, it's minus. And time comes first because we're always moving through time more than we're moving through space. That's called space-like. Oh, sorry, that's called time-like because time dominates space. If they equal each other, then you're moving at the speed of light. That's light-like. And if space dominates, then it's impossible. That is space-like because then you're moving faster than the speed of light. So here's kind of our coordinate system. Here's what it means. Here's the space-time interval. This is really, really important that that's constant. This is the universal constant. Sorry. This is a universal invariant. I like that word better. It's cooler word, sounds more advanced, right? It's universal invariant. This comes from the fact that the speed of light, of course, is also a universal invariant, but space and time are not. There is no universal time. There is no center to the universe. There is no universal reference frame. This has been shown again and again in experiments to be the case that all reference frames measure the speed of light and that space and time themselves are what change. Cool. That's the starting place. So what we did after this, pause and make sure that makes sense, right? Is do what are called Lorentz transformations. And I have the sheet that I handed out that helps us practice this. And the Lorentz transformations just simply transform, and this is straight up a coordinate. This is not dx. It's only dx prime when obviously x prime initial is 0, which is usually the case. So we can usually exchange this with dx prime if our starting place is the origin. That's why I typically do that. Remembering that we have some velocity v, x and t are the stationary frame, x prime is the moving frame, and gamma is the relativity factor, 1 minus v squared over c squared. We are setting c equal to 1, and v is in terms of c. That makes this really easy. No meters. We are dealing with seconds. It means x is then light seconds, t is seconds. Great. That means t prime simplified is going to be t minus vx. Technically, there's a c, c, and c there. You'll see that on the note sheet itself, but this is the simple way to remember this shorthand because c equals 1. Done. You know these formulas. This is what we're doing. Great. So what I'm going to do is we're going to do a little graphing right now. Do, 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 do. Did it. Ready? All right. We're going to do Desmos because Desmos is awesome. All right. So here's what I did here, although I need to undo some things. What we did is we solved for points of constant time in the moving reference frame. So I'm going to give some context. We did this on the sheet in class. I'm going to quickly go through the context here, right? The context is this. V is 0.8 C, right? Gamma, therefore, is 1 over the square root of 1 minus 0.8 squared, which ends up being 5/3 if you do it in fractions, which I highly recommend. So gamma is 5/3. Great. I've graphed the world line, and the world line we always want to remember is defined by x prime equal to 0. This is huge. This is almost equally, in fact, I would say almost more important than that the speed of light is the same in all reference frame. What does this say? This says x prime equals 0. What does that mean? It means that within its own reference frame, it's not moving. An object, feel this as you walk down the street. Are you ever moving relative to yourself in your own reference frame? No, the buildings are now behind you. Some buildings are coming towards you, right? Your positive velocity is in your reference frame 0 and manifests as everything else having a negative velocity towards you. Realize that that's exactly the same thing, and that's exactly what's happening. Enter that space-time switch. Very powerful, very powerful. An object is never moving relative to itself. Let that sink in. You can pause the video. That is huge. This is like a huge, this is like relativity 101. This is like the basis of it. A world line, an object is never moving relative to yourself. So this is where the object is. Not what the object sees necessarily. Obviously, it sees this. X prime T prime can be outside of itself. It can see other X primes. It can see an X prime two light seconds away from itself, 2 meters away from itself. You know, left or right, up or down, back and forward in time, right?
it can see, it's like what the moving object sees is different than where it is. Obviously, I'm here, but there's a world around me, and I say, okay, that's 3 meters away from me. That has an x prime of 3 meters, right? What moving object sees. So be careful. So x prime equals 0, if we plug that into our Lorentz transformation, please look at those equations right now with your eyes. Boom, laser eyes, there's my eyes. Gamma, x minus vt. Say it in your mind. Gamma is 5/3. X minus zero point 0.8, I'll write it as 4/5 t. You solve for t, you get t equals 5/4 x. That is this line right here. Boom. Right? I'm going to get rid of those. That's all sloppy. Cool. I'm clearing this all. Write it down. Pause the video. Clear all drawings. This is the world line of x prime equals 0. This one right here. All the way down to the origin. So that's where the object is. These green lines, this dotted line is v equals c, just for reference. That's the speed of light. If you go slower, this is a slower world line. Because remember, this is the time axis, this is the x-axis. Slower obviously means that you're moving more through time than through space. This is space-like over here. This is impossible. You'll then say, well, why is this line over here? Here's why. This is the t prime equals 0 line. The t prime equals 0 line is important. I'm going to get rid of these. You'll notice it's like a mirror image on, I'm just going to erase this one. You'll notice it's a mirror image across the light line, right? This is the light line, meaning V equals C. Whoop. That's this one, right? Of x prime equals 0. These will always be opposite slopes. If you plug in to the Lorentz transformations of t prime equals 0, you get t equals 4/5 x. What does this mean? This means that this point, this point, this point, and this point all happened at the same time. They all happened according to the moving rocket or moving observer, whatever imaginary thing you want going at 80% the speed of light. It's always a rocket, right? So the rocket sees itself, right? It's forward and backward, right? Its front will be here, its back will be here, right? It's moving at different x positions. Some are in front of it, some are behind it, but its middle is at x prime equals 0, and it's moving this way. But it sees these points all happening at t prime equals 0, which of course started here. This was where the rocket started, and it's moving this way. All of these happened at t prime equals 0. So if it went from here to here in its own reference frame, that would be infinite speed. So of course this is in the space-like region because it's impossible. It's also impossible to instantly move in space and not move in time. So as it moves through space, time progresses for it as well. And that's what these lines are. So this is t prime equals 1. You'll notice that at t prime equals 1, where's the rocket? Look at where t prime equals 1 is. Look at where the world line is. T prime equals 1 says that, okay, at t equals 1 second for the rocket, which is tau. Remember, tau is the time inside the moving object. So t prime turns into tau when x prime is 0. Pause and let what I said just make sense. Remember, x prime, t prime are what the observer sees, the moving object sees. But this could be outside of itself. It can see something outside of itself happen at a different time.
Like I'm seeing somebody else walk down the street. That's not my internal time. I'm claiming that that person did something at a specific time. I see it. I measure it with my clock. Said, hey, that guy's eating a hamburger. You ever seen Mitch Hedberg? That guy's eating a hamburger right now at 30 seconds, right? But that's not my own world line. When it's my own time, right? This becomes tau when x prime equals 0. But x prime can be anything. X prime, I could see something 5 meters away from me have some other different happen at a different time. Does that make sense? So when x prime equals 0, this is called the proper time. This is one of the most important concepts in existence that all observers agree on the proper time. All observers will agree that 1 second was observed for this rocket inside itself, right? But the rocket will never experience all of these moments because it only was here. It was here. This is x prime equals 0, t prime equals 0. So this was tau equals 0, right at the origin. T prime equals 0 are all these other points that happened in the city, happened in the universe. Maybe there's a distant star over here, and it said, yeah, when I left my rocket ship, that star was experiencing time equals 0 here. The issue is, check this out. If in the Earth's reference frame, that star was here. What? Same position. Obviously, these are the same x position. This is the x-axis, different time position, which means that what the rocket sees is the same time, the Earth sees it happening at a very different time. This is now time equals 6, when this is t prime equals 0. Wow. Which means simultaneity is relative. Things don't happen at the same time for different observers. Now, in that specific reference frame, it's certain what simultaneity will look like. So there is a absolute truth in each reference frame, and the truth of experience is a function of reference frame. So it's not unpredictable, it's very predictable. We're not doing quantum mechanics yet, right? In special relativity, it's determined, it's predictable what time you're going to experience, but it's relative, meaning that somebody moving will experience a different simultaneity than somebody who isn't. So this sun exists, this star exists, it's moving through space and moving through time. Let's say it's stationary in space and just moving through time. The rocket will experience time equals 0 to be here, but the Earth will experience that moment as time equals 6 seconds. And it will experience time equals 0 as here, because that's time equals 0. So you just got to read the graph. The point is we're just reading the graph. Let that bake your brain. It's kind of crazy, but we're just reading the graph. So here's the point. Question 3 on the sheet is what I'm doing right now. We're going to mark. So let that bake in, but like pause for a second. We're just going to do a simple thing. Bring it back. Bring it back. I'm going to mark 1 second intervals. We already just did that. Notice that t prime equals 1 second, right? Is where you plug in 1 equals gamma t minus Vx, and you solve for t. You should get t equals uh, 1 over gamma plus Vx. It's pretty easy algebra there. 1 over gamma, right? Plus Vx, right, is going to give us this uh, this line right here. And you'll notice that that 1 over gamma is 3/5, which is 0.6. Indeed, that is 0.6. And we're doing a slope of 4/5 because that's V. V is 4/5. Remember, gamma is 5/3. Great. Let's write that down. Always good to write down your information. Great. We have this. So all points along this line are 1 second later on the rocket. Notice where the rocket is, that is tau equals 1 second. Only where the rocket is that tau. Everywhere else it's called t prime. So this is 1 second in space-time. Because x prime equals 0, tau equals 1 second, that's a total space-time distance of 1. And we'll say 1 light second, which means that Earth went a different distance. How far did Earth go? Well, it's pretty easy to see. We can ask Desmos, right, where that point is. Well, that point is going to be, that's the x coordinate, but that's the t coordinate, 1 2/3. Wait, what's 1 2/3? Wait, that's gamma. Oh my God. So we actually could get this in a different way. Let me clear. So that's not coincidence that that's gamma, right? How else could we get this? So to get the tick marks are the time marks, right? So to mark the points of d tau equals 1 second, right? What you do is you use the time dilation formula. So the time dilation formula is d tau equals the square root of 1 minus v squared over c squared dt. Please know this. This is the last formula. This is the same thing as the space-time interval, but we're solving for d tau in terms of dt. And I'll refer to the last video and our class notes for exactly how to derive this, but it's pretty straightforward. So I want d tau to equal 1 second. So 1 equals the square root of 1 minus 0.8 squared dt. Well, this is 1 over gamma. So dt is going to equal gamma. It's going to equal 5/3. You can just quickly do that arithmetic. You get 5/3. Great, which means that for every 1 second in the rocket, 5/3 or what's that? 1.6666, right? Seconds evolve in, so this is, wait, look at me like this is 2, so this is 1 right here. So this is 1, this is 1.5, 1.75, so 1.66666 is like right here. Oh, look, matches up perfectly. So tau equals 1 second is the same as 1.6 or 5/3 seconds. I'm just going to write it exactly as a fraction, right? In we'll say the Earth's reference frame or the stationary reference frame. This is time dilation. It's crazy, right? That the rocket literally experiences less time because it's moving through space. The total speed of light, so total speed of anything through space-time is c, right? And so if you move more through space, you move less through time. That's this hyperbolic geometry. Hyperbolic meaning it's a minus sign, right? That this is dt squared minus d x squared. So remember, d tau comes from ds squared over c squared. That's d tau squared. And it's defined when dx prime is 0, or just x prime is 0. Right? An object moving relative to itself is 0, so it only experiences time. That time is called proper time. Let that make sense. This is an official definition. I'm not saying it as a tangent, just reminding you this is where this comes from. It's huge. So let's look at this a little differently, right? So let's clear it all and let's mark, okay, here's 1 second, and let's add this one. Let's add the 2 second one, and let's add the 3 second one. All right, so this was t prime equals 0, t prime equals 1, t prime equals 2, t prime equals 3. We've graphed those lines, right? Notice that it intersects them here, here, and here. So this is tau equals 1, tau equals 2 seconds, tau equals 3. What does that mean? The time elapsed in the rocket. How much time elapsed in the Earth's reference frame? Well, it's 5/3 seconds on the Earth here. Don't think too hard. Here it's going to be 10/3 seconds. What is that? 3.33333. So 3 1/3 seconds here. And then 15/3. Don't think about that too much. That's 5 seconds here. And indeed, this point is 4, 5. Now 4 comma 5 in xt, x and t are the outside observer, will of course be a velocity of x over t, or dx over dt technically. 4 over 5, that's 0.8 the speed of light. Because this is 4 light seconds in 4 seconds. So confirming, of course, this world line is indeed 4 light seconds in 5 seconds. Boom. So this is what we do. These are the tick marks. 1 second, 1 second, 1 second. Now ready to be tripped out? Here's the crazy part. Let's do it. This distance is 5. This distance is 4. So remember our space Pythagorean theorem that if I go 5 meters and 4 meters, my total displacement is the square root of 41, which is what, 6.3 meters? Not in space-time. This is true in space. Check. That is true in space, but not in space-time. Meaning to have the speed of light, which is motion of space through time, be the same in all reference frames, time has to be different. Time and space are connected in a hyperbolic geometry. Hyperbolic meaning ds squared equals dt squared minus dx squared. This minus sign is hyperbolic. It's a hyperbola. Not a circle. It's not a radius of a circle where you have, x squared plus y squared equals z squared equaling the same thing, right? We're not doing that, right? There's no circle here, right? It's a hyperbola. The point is, this is 5, this is 4. What's this distance? 3. Isn't that crazy? 5, 4, 3. And it's corresponding to our t prime equals 0, t prime equals 1, t prime equals 2, t prime equals 3 lines that we graphed in class. That's these dotted green lines here. Isn't that amazing? I think that's amazing. That's amazing. Ready? It's going to take it one more step. Ready? Pause it if you need to. That's it. That this distance from here to here is 3. And that all observers agree on that is 3. You might disagree on the actual space-time coordinates, but this distance is 3 in all reference frames. I'm about to prove it to you, at least show you one step in proving it to you. Ready? xt equals 4, 5, right? This is 4 comma 5 in the stationary reference frame. What is it in the rocket's reference frame? Well, we just mapped it, but let's do the Lorentz transformation and see if we get the same answer, right? So x prime is gamma times x minus vt, which is going to be 5/3 times x, careful, x is 4, minus 0.8 times 5, 0.8 times 5, I could do 4/5, same thing, is 4, 4 minus 4, oh, it's 0. Cool. That should make tons of sense. Da, 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 da. Why does that make sense? This is x prime equals 0. This is the world line. Whoa, of course it's x prime equals 0. Bum, bum, bum. How about t prime? We already figured it out because if x prime equals 0, t prime is tau. But let's see if the Lorentz transformation works. 5/3 t minus vx, careful, it's backwards for the time one. 5/3 t is 5, look with your eyes, t is 5 minus 0.8 times 4. You can do that in your head. 0.8 times 4 is 3.2. 3.2, my 5 minus 3.2, 1.8. So this is 5/3 times 1.8. 1.8 divided by 3 is 0.6. 0.6 times 5 is da 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 da. What? This is 0.3. Of course it is. It's 0 in position, and it's, what was it? 1, 2, 3 seconds in time. So notice that this is tau equals 1, tau equals 2, or I say d tau equals 1 for all of these. D tau equals 1, d tau equals 1, d tau equals 1. Whoa. I guess technically this is dt prime, but in the world line of the object, it was tau. Tau equals 1, tau equals 2, tau equals 3. Notice t prime equals 1, t prime equals 2, t prime equals 3. Boom. ds squared equals dt squared minus dx squared. C is 1. T, look at it. T is 5, x is 4. T is 5. 5 squared minus 4 squared. 25 minus 16 is 9. If we do it with the primes, what do we get? dt prime squared is 3 squared is 9. 0 squared is 0. What do you get? 9. If we switch to any reference frame and we did its diagonal lines and ask where this point is, it would yield a result of t and x such that its triangle, right, yields 9 along this world line. All observers agree that this rocket experienced 3 seconds in itself, that relative to itself, it experienced 3 seconds. That is universal. Let's do one more. Let that be, that's just that, oh, that's so good, right? Let's do one more. So I'm going to do a point 3, comma 3. If we graph the other axes, meaning we graph the time axes, the space axes, x prime equals 1, x prime equals 2, x prime equals 3. And I'm going to zoom in on this point here, 3, 3. Look at what lines those are. We're practicing reading the lines, right? So this is x prime equals 0 right here. This line here is x prime equals 1. This line is x prime equals 2. I made them a different color for your convenience. X prime equals 3 and x prime equals 4. Which line is this on? This is on x prime equals 1. So xt equals 3, 3 in the Earth's reference frame, 3, comma 3. That's what these lines are. These lines are constant time and constant space, right? But these diagonal lines are lines of constant time and constant space in our boosted rocket reference frame. It calls a boosted reference frame, right? The green lines, remember it's going to get a little wacky, but we got it. T prime equals 0, T prime equals 1. If you look at this long enough, you realize, oh, wait, that is pretty clear that this is along x prime equals 1 and T prime equals 1. So we should expect x prime T prime to be what? 1, 1. Let's see if the formulas give us that. X prime equals 5/3 times 3 minus 0.8 times 3. 2.4, that's 0.6, that's 0.2 times 5 is 1. If you do that arithmetic, do it by hand. I challenge you. Don't use a calculator. If you do the same thing for t prime, you realize it's the exact same number because it's still 3 minus 0.8 times 3 times 5/3. You get 1. 1, 1. So it happened 1 light second away after 1 second in the rocket's reference frame. This is say the Earth and the rocket both see some explosion. Some other rocket exploded. Wow, right? Love explosions. In the rocket's reference frame, right? That happened 1 light second away after 1 second. In the Earth's reference frame, it happened 3 light seconds away after 3 seconds. Crazy, right? Now, that object was traveling how far, how fast? Now, this is almost, I shouldn't have said it exploded, because technically what's about to happen can't explode. Maybe a poor example, right? So, in other words, let's look at what is the distance along this line. Well, it's going to be 3, 3. Is it the square root of 18? Remember, we have 3 and 3. In space, it's 3 squared plus 3 squared. If I have 3 meters and 3 meters, I go the square root of 18, which is 3 root 2 meters.
Great. But this is space-time. So I do time squared minus space squared. I get ds squared is 3 squared minus 3 squared, which is 0, which means this is tau equals 0. This is the speed of light. The speed of light experiences no time because it goes through time and space equally, and those cancel each other in the hyperbolic geometry. This is the only way for light will never observe anything. Light will never observe the speed of light. For light to see the speed of light be the same in all reference frames means it can't experience time at all. It can't experience space-time at all. It's called a null trajectory. What? That's crazy, but it's very real. Light experiences no time. It cannot. Notice that in the 1, comma 1, if we do it in the rocket's reference frame, we also get 0, confirming the space-time interval is the same for all reference frames. X and t might be different than x prime and t prime, but if you subtract their squares, you get the same number. Boom. Universal constant in all reference frames is the space-time interval. I'm going to let this make one more piece of sense and then we're done. If x equals t, then x prime equals t prime. Because then both observers will see dx dt equal 1 and dx prime dt prime, that's supposed to be a prime, sorry, equals 1, meaning it equals the speed of light. 1 meaning 1 times the speed of light. Remember, because velocity is in terms of light speed. Sorry if that gets missed. So 3 over 3, still 1. 1 over 1, still 1. The point is the speed of light, right? 1 comma 1 yields a speed of light in the rocket's reference frame of 1 times the speed of light. Thus showing that even in the rocket's reference frame of, oh, it happened 1 distance away after 1 second, right? Notice that that's kind of wonky how that works, right? 1 distance away after 1 second. Or I guess it would be 1 distance away. Hey, how does that work? I'm trying to figure that out. 1 distance away after 1 second. Like that? Whoa. So this is the distance, this is the time. This is 1 light second, 1 second. I don't know. I'm trying to make sense of that, of how that's manifested. The point is it's 1 comma 1. That means it went 1 light second per second, one speed of light. Boom. Speed of light's the same in all reference frame. If x equals t, x prime equals t prime, space-time interval, therefore, in that case is 0, right? That is the speed of light. Boom. It's the universal constant. Let's do one last thing, actually. One more bonus thing. This one's just kind of cool. Look what happens to these axes if I change the velocity. Let me go down to 0. It becomes the Euclidean spacetime. And as I go faster, notice this is 10% the speed of light, right? Oops. Notice what happens to these axes, right? Notice that it's going, yes, right? 0.75, 0.8. It's going, what is it? Oh, here we go. Here's how I would do it. Because you'd go up 1 second in the world line over 1 second, right? So it's going to go like this, right? Right. Up 1 second over 1 second or over 1 light second. That's how it is, right? Because this is 0 comma 1 and this is 1 comma 1. Isn't that cool? So you go 1 second this way along the world line, 1 second, 1 light second over along a constant time axis. Isn't that cool? So these points happen along the same t prime equals 1. These points happen at the same time in the rocket's reference frame. Isn't that crazy? That's amazing. It's amazing. All right, pause this video, rewind it, let that make tons of sense. Let's go to the speed of light, though. This is really cool. What happens to all of the axes as you go to the speed of light? They all collapse on the light line, world line. No time, no space experienced. Welcome to the universe. I love you.
Namaste.